Welcome to MSB lecture series on the chemistry of main group elements. In my previous lecture, I had discussion about oxo acids of phosphorus and I gave information about phosphinic acid and phosphonic acid. Let me introduce two more phosphorus acids, that is hypophosphoric acid and ultimately orthophosphoric acid. Let us look into hypophosphoric acid first. Hypophosphoric acid has formula H4P2O6. Okay. The reaction between red phosphorus and NaOCl or NaClO2 yields Na2H2P2O6. Okay. Dehydration using P4O10 gives H4P2O6. That means dehydration using, if you take this one and if you perform dehydration using P4O10, that gives H4P2O6, and the first indication of a PP bonded dimer came from the observation. The acid was diamagnetic and X-ray diffraction data for the salt was found to have this composition. So, that means all terminal PO bonds are of equal length, that is 157 picometer, and in hydrolysis it gives two types of acids. Now, let us look into phosphoric acid, and one can prepare phosphoric acid by treating calcium phosphate with sulfuric acid. So, one can prepare by treating calcium phosphate with sulfuric acid. Okay. So, pure acid forms deliquescent colorless crystals with melting point 315 Kelvin. Is white crystalline solid. It has a molecular structure with POH and PO bond, distance of 157 and 152. So, let me write the structure for you. Okay. So, here this PO bond distance is 152 and this is 157 PO bond, 157 picometer. This is 152 picometer. In dilute aqueous solution, acid molecules are hydrogen bonded to water molecules rather than to each other. So, that means essentially in aqueous solution we do not come across intramolecular hydrogen bonding, instead we come across hydrogen bonding with water molecules. Phosphoric acid is a very stable and has no oxidizing properties except at very high temperature, aqueous phosphoric acid is a tribasic acid due to the presence of 3 OH groups. When phosphoric acid is heated to 510 Kelvin, it is dehydrated to diphosphoric acid, that is H4P2O7. So, when phosphoric acid is heated to 510 Kelvin, it forms H4P2O7 plus H2O, and further heating yields triphosphoric acid. Of course, these reaction can be represented in a simple way. For example, okay, so one can write something like this, and another one, okay, and essentially here condensation takes place through the elimination of water molecule. Okay, and of course, here one can write like complete structure. Here it can be so. This is how one can start writing, having POP linkages, polyphosphates or polyphosphoric acid. Okay. So, now with this let us begin discussion on polyphosphates. If acid phosphates such as NaH2, PO4 or Na2H, PO4, so containing essentially POH groups are heated, condensation reaction occurs to form POP linkage via elimination of water to form polyphosphates. So, in a very simple way one can represent these reactions in this fashion to form POP linkages through the elimination of an equivalent of water for the condensation of 2 POH bonds. So, when disodium hydrogen phosphate is heated, the pyrophosphate is formed. Okay. So, pyrophosphate is essentially P2O7 4 minus. If you are curious to know the structure of this one, it is very simple to write. Okay. So, if you count P2, 1, 2, 3, 4, 5, 6, 7 and 1, 2, 3, 4, 4 negative charges are. So, this is pyrophosphate. So, if you have one POP linkage, they are called pyrophosphate. If sodium hydrogen phosphate is heated, since each phosphorus has 2 POH groups, then cyclic phosphate can also be formed. So, if we involve the condensation of 2 OH groups per phosphoric acid, that can lead to the cyclic or linear polyphosphate, and here in case of cyclic phosphates we can have up to 10 phosphorus atoms. That means, cyclic phosphates having 10 phosphorus atoms in a cyclic system are known. You can see here this is pyrophosphate, and of course, here if you involve the condensation of 2 OH groups per phosphoric acid, you can get either trimeric or you can get tetrameric. Up to having 10 phosphorus atoms in the cyclic system are known. They are essentially called polyphosphates, and linear polyphosphates containing long chains of PO 3N N minus. One can consider here, if you consider here as a monomer, this is PO3N having 1 minus charge. So, one can conveniently show the monomeric unit in this one, something like this. So, in this one what one should consider is this one is a monomeric unit, and if you consider this as a monomeric unit, we can write comfortably PO3 N and N minus. So, N is 1, this is also 1. So, this how and of course, here by adding PO3 2 minus groups, we can terminate heating a mixture of HPO 4 2 minus and H2 PO 4 minus. So, we can control the chain length, and of course, here now if I want to add, I can keep on adding HPO 4 2 minus, and then if I want to terminate, you add another one having only one OH group, so that it links and the chain growth is terminated. Okay. So, when P3O9 3 minus is treated with OH minus ions, one of the POP group undergoes hydrolysis, giving the triphosphate. So, it continues, and of course, this triphosphate is used in detergents, is very important in detergents, this is used. Okay. Of course, for example, if I take a cyclic one here, okay. So, this essentially gives this one. Okay. Yes, you treat this one with OH minus, one can conveniently get this. So, this is essentially P3 O10. You can count the charge now 1, 2, 3, 4, 5, 5 minus, one can write. Even if you do not know the charge here, once we know the composition, we know that in these compounds the oxidation state of phosphorus is 5. So, that we should be able to write here. Okay. For example, this one P is accounts for P3 is 5 into 3 equals 15, and this is 10 into 2 20, and then the deficit is 5. So, you can have 5 minus here. So, you can find out this charge on it very easily. Okay. So, polyphosphates one can explain in a very similar way to polysilicates. So, we have here PO4 3 minus tetrahedra, there we had SiO4 4 minus tetrahedra, because there all are terminal bonds, whereas here one of the PO bond is P double bond O, it does not have any charge. So, it is PO4 3 minus is similar to SiO4 4 minus, and this is how the tetrameric structure can be represented in this fashion here. The simplest condensed phosphoric acid H4P2O7 is a solid at 298 Kelvin and can be obtained from reaction of PoCl3 with H3PO4. If we treat phosphoric acid with PoCl3, it leads to the formation of H4P2O7. Okay. And it is much more stronger than phosphoric acid. The sodium salt Na4P2O7 can be obtained by heating Na to HPO4 at 510 Kelvin. Of course, here Na4 essentially you replace all OH with ONA, you will get the sodium salt. Okay. The acid refers to as metaphosphoric acid with an empirical formula HPO3 here. It is actually a sticky mixture of polymeric acids obtained by heating H3PO4 and H4P2O7 at 600 Kelvin. So, that means if a mixture of H3PO4 and H4P2O7 is heated to 600 Kelvin, it gives metaphosphoric acid having composition HPO3. Okay, you can see some of the all oxoacid structures I have shown here. This is phosphinic acid. You can see here it is monobasic acid because we have one OH group and of course 2 pH groups, and then phosphonic acid we have 2 OH groups. So, it is a dibasic acid, and phosphoric acid has 3 OH groups, it is tribasic acid. Okay. Similarly, hypophosphoric acid, if you see here it has 4 of them, so it is a tetrabasic acid, and similarly diphosphoric acid H4P2O7 we have 1, 2, 3, 4, it is also tetrabasic acid, and similarly H5P3O10 triphosphoric acid we have 1, 2, 3, 4, 5. So, this is pentabasic acid. Okay. So, now let us look into oxoacids of arsenic, antimony and bismuth. Arsenious acid, that is ASOH thrice or H3ASO3 has not been isolated so far. So, that means ASOH thrice or H3ASO3 is not isolated. Okay. So, aqueous solution of AS2O3 probably contain H3ASO3, and arsenic acid similar to phosphoric acid, thus H3ASO4 is obtained by dissolving AS2O5 in water or by oxidation of AS2O3 using concentrated nitric acid. So, you can see here AS2O3 on treatment with concentrated nitric acid gives H3ASO4. Oxoacids of antimony are not stable and few antimonate salts are well characterized. So, no oxoacids of bismuth are known, although some bismuthate salts are well characterized. So, sodium bismuthate is an insoluble orange solid obtained by fusing Bi2O3 with sodium hydroxide in air or with sodium peroxide. Now, let us look into the sulfides and selenides of phosphorus. Although the structures of the sulfides appears to be closely related to those of oxides, but there is remarkable difference is there. For example, P4O6 and P4S6 are not isostructural. You are already familiar with the structure of P4O6. In a couple of minutes, I will be showing you the structure of P4S6. You can see the differences in the structure. That means, although they appear similar, they are not isostructural. The bond distances within the cages of all the sulfides indicate single PP and PS bonds. The terminal PS bonds are always shorter because of having PS double bond. the reaction of red phosphorus with sulfur above 450 Kelvin yields this phosphorus sulfides such as P4S3 and P4S7. Above 570 Kelvin, white phosphorus combines with sulfur to give P4S10, similar to phosphorus thiopentoxide, which is the most useful of the phosphorus sulfides. Okay. So, these are the structures you can see here, and of course, in case of P4O6, this PP bond is not there. In place of PP bond, we had a POP bond. So, in case of P4S6, what we have is we have a PP bond intact, and then the sulfur is oxidizing one of this one. As a result, what happens? We have 3 trivalent phosphorus and 1 pentavalent phosphorus, and similarly P4S7 still PP bond is intact, and only in case of P4S9 that PP bond is changed to PSP bond, and then here we have 3 phosphorus are in pentavalent state and 1 phosphorus in trivalent state. In case of P4S10, you can see it is very similar to P4O10. And you can see here P4S3, we have 3 PSP bonds, and P4S4, of course, another PP bond is broken, and in case of P4S4, we also have a different one, beta P4S4, and in case of this one, we have 1 PP bond intact and one of the phosphorus is in pentavalent state P4S5, and similarly we can also have a P4S5 of different structure, where except 1 PP bond, all PP bonds are broken with PSP bond. So, this is where the structural similarities between phosphorus oxides and phosphorus sulfides can be looked into. Okay. And phosphorus sulfides ignite easily, and P4S3 is used in strike anywhere matches, and essentially it is combined with KClO3, and the compounds inflame when subjected to friction. Whatever we have in matchbox, it has a combination of P4S3 plus KClO3, and on striking, okay, it catches fire. So, P4S3 is stable to water. So, other phosphorus sulfides are slowly hydrolyzed. So, what would happen when we treat phosphorus pentasulfide with water can be seen from this equation. So, reactions of phosphorus pentasulfide is very similar to the reaction of phosphorus pentoxide with water. So, instead of 10 equivalents of water, what we are getting is 10 equivalents of hydrogen sulfide, and similar to phosphorus sulfides, phosphorus selenides are also known. For example, P2 SE5 and P4 SE10 are known, and P2 SE5 structure can be written in this fashion. Of course, this kind of properties stems from the fact that chalcogens are known for undergoing catenation. That is the reason we see here having SE-SE bonds, and thus the composition is P2SE5. And of course, these compounds can be made by direct combination of white phosphorus with selenium under appropriate reaction conditions. In fact, arsenic and antimony sulfide ores are the major sources of group 15 elements. In the laboratory, As2S3 and As2S5 are usually precipitated from aqueous solutions of arsenides or arsenates. Reaction proceeds when H2S is passed slowly through the solution at 298 Kelvin. Okay. Of course, here concentrated acid, if the temperature is lower to 273 Kelvin and the rate of flow of H2 is increased, one can get As2S5. Same reaction if it is carried out at a lower temperature with a high flow rate of H2S, one can get As2S5 instead of As2S3. Okay. And the sulfides of arsenic such as As4S3, As4S4, and As2S3 occur naturally. Let me show you the structure of As2S4. So, you should while writing structure, you should make sure that all arsenic atoms are trivalent, and whereas sulfur or chalcogens are divalent, and this distance is 249 picometer and this is 223 picometer. Okay. The bond distances in alpha As4S4 are consistent with ASAs and ASAs single bonds. So, in this view of the cage allows a comparison of S4N4. Of course, S4N4 compounds are very similar in structure to S4S4. The only well characterized binary sulfide of antimony is the naturally occurring ore stibnite, that is Sb2S3. Okay, let me stop here, and in my next lecture I will be discussing on another important type of compounds of phosphorus and nitrogens, that is called phosphogenes. Until then, have a very pleasant reading of group 15 chemistry. Thank you very much.